Hello everyone, welcome back to our channel. In this video, we'll explore two groundbreaking technologies revolutionizing artificial intelligence: Model Context Protocol, MCP, and Retrieval Augmented Generation, RAG. In today's rapidly evolving AI landscape, these innovations represent critical building blocks for creating truly intelligent systems that can access real-time information and take meaningful actions. MCP, developed by Anthropic, provides a universal standard for connecting AI models to external tools and data sources, much like a USB port for AI, while RAG enhances AI responses by grounding them in external knowledge. Throughout this presentation, we'll define both technologies and their core components, examine how they complement rather than compete with each other, explore real-world examples across industries from software development to financial services, investigate social media integrations, and demonstrate how enterprises can leverage these technologies for competitive advantage. Together, they're addressing fundamental limitations of traditional language models and opening new possibilities for enterprise applications. Join us as we demystify these technologies and reveal how they work together to create more capable, reliable AI systems. What are MCP and RAG? First, let's examine the Model Context Protocol, MCP, from Anthropic. MCP is an open protocol, meaning anyone can use it. It was developed by Anthropic, and it standardizes how AI models connect with external tools, data sources, and services. It creates a unified layer between large language models, LLMs, and external systems, allowing AI assistants to access real-time information and perform meaningful actions. MCP works through a client-server architecture. MCP clients. These are applications like Claude Desktop, Cursor, or Windsurf that want to use external tools. MCP servers. These are lightweight programs that expose capabilities of specific tools or data sources. And protocol. This is the standardized communication method between clients and servers. MCP allows large language models to access various tools without needing custom integrations for each one. For example, an AI assistant can use an MCP server to search the web, access files on your computer, or connect to databases. Now let's look at Retrieval Augmented Generation, or RAG as it's called. RAG is a framework that enhances LLMs by connecting them to external knowledge sources. Rather than relying solely on the information contained within the model's parameters, RAG enables the model to retrieve relevant information from a knowledge base before generating a response. The basic RAG process works as follows. 1. A user asks a question. 2. The system converts the question into a query vector. 3. The query is used to search a vector database for relevant documents. 4. Retrieved documents are provided as context to the LLM. 5. The LLM generates a response based on both the question and the retrieved context. RAG helps address limitations of LLMs by providing up-to-date information and reducing hallucinations by grounding responses in specific retrieved content. Are MCP and RAG complementary or competing technologies? The answer is MCP and RAG are not competing technologies, but are highly complementary technologies. They serve different purposes in the AI stack. RAG is a methodology for retrieving and using external information to enhance LLM responses, while MCP is a standardized protocol for connecting LLMs to various tools and data sources, which could include RAG systems. In fact, MCP can make implementing RAG systems easier by providing a standardized way for AI models to connect to vector databases and other knowledge stores. For example, an MCP server could be created to connect an AI assistant to a vector database containing a company's documentation, implementing a RAG workflow through the MCP standard. So when do you use MCP versus RAG? Here's when one should use MCP. Tool integration. When you want your AI assistant to use multiple external tools, like file systems, web search, and APIs. Real-time data access. When the AI needs to access the latest information or dynamic data sources. Action execution. When you want the AI to perform actions, like sending emails, creating calendar events. Developing AI applications. When building applications that need to connect to various services and systems. And here's when to use RAGs. Domain-specific knowledge. When you want to enhance an AI with specialized information not in its training data. Up-to-date information. When you need the AI to access current information beyond its training cutoff. Factual grounding. when accuracy is critical and you want to reduce hallucinations. Information retrieval, when the main goal is to find and present relevant information from a specific corpus. Many advanced AI systems will use both technologies together. For example, an AI assistant might use MCP to connect to various tools, including a RAG system that retrieves information from a company's knowledge base. The key difference is that RAG focuses specifically on information retrieval and context enhancement, while MCP is a broader protocol for connecting AI to any kind of external capability. What is the business value for enterprises to adopt MCP and RAGs as an essential part of their AI strategy? Why should organizations seriously consider these technologies? For enterprises, MCP and RAG technologies represent a pivotal shift in AI adoption and value creation. They will enable the development of specialized agentic AI agents to boost productivity and efficiency. Moreover, these technologies address core business concerns about AI deployments: reliability, accuracy, and integration with existing systems. RAG ensures that AI systems can leverage proprietary knowledge bases, compliance documentation, and internal expertise, rather than relying solely on general training data, dramatically reducing hallucinations and enabling domain-specific expertise. Meanwhile, MCP allows these AI systems to seamlessly connect with enterprise tools, from CRMs and ERPs to specialized industry software, without extensive custom development. Organizations implementing these technologies can expect accelerated development cycles, reduced integration costs, and autonomous AI systems that truly understand their business context. Forward-thinking companies are already creating MCP servers for their internal tools and building RAG systems on their proprietary data, establishing competitive advantages through AI that genuinely understands their operations and can take meaningful actions across their technology stack. Let's now look at some real-world examples of MCP in action. Model Context Protocol, MCP, has been gaining rapid adoption since its introduction by Anthropic. Here are some concrete examples of how MCP is being used in the real world. Number 1. Claude Desktop Application. One of the most accessible examples is the Claude Desktop app, which uses MCP to connect Claude to various tools and data sources. Users can install MCP servers that allow Claude to access and search through local files on their computer, perform web searches via Brave Search to get up-to-date information, read and analyze Git repositories, access database information through PostgreSQL or SQLite connections. This transforms Claude from a standalone chatbot into an assistant that can interact with your local environment and the web. Number 2. Development environments and coding assistance. Several coding-focused applications have embraced MCP. Cursor, this AI-powered code editor, uses MCP to connect to GitHub, file systems, and other development tools. This allows the AI to understand codebases, suggest changes across multiple files, and help with programming tasks. Windsurf Editor, an agentic IDE that uses MCP to integrate AI with developer workflows, allowing for collaborative AI interactions while maintaining developer control. Continue, an open-source AI code assistant that supports MCP across VS Code and JetBrains IDEs, allowing developers to access various tools directly in their preferred development environment. Number 3. Enterprise Tool Integration. Companies are building MCP servers for their enterprise tools. Cloudflare has created an MCP server that lets AI assistants deploy and manage resources on their developer platform. Stripe offers an MCP server that enables AI agents to interact with the Stripe API for payment processing. Axiom has developed an MCP server that lets AI assistants query and analyze logs, traces, and event data using natural language. Number 4. Knowledge management and research. MCP is being used to connect AI to various information sources. Obsidian Markdown Notes has an MCP server that allows AI assistants to read and search through notes in Obsidian Vaults, enhancing knowledge management workflows. Weaviate offers an MCP server that enables AI agents to implement semantic memory through their vector search engine, effectively creating an MCP-based RAG system. Number 5. Specialized industry applications. MCP is enabling specialized tools in various domains. Google Maps, MCP Server provides location services, directions, and place details for AI assistants. Everart uses MCP to give AI access to image generation capabilities using various models. AWS KB Retrieval allows retrieval from AWS Knowledge Base using Bedrock Agent Runtime. Number 6. Community-built extensions. The open nature of MCP has led to community-developed servers for various tools. Spotify MCP Server allows control of music playback and playlist management. Docker MCP Server enables management of containers, images, and networks. Kubernetes MCP Server for managing cloud infrastructure. Todoist MCP Server for task management integration. The rapid growth of the MCP ecosystem demonstrates how standardization is accelerating AI tool integration, rather than each AI company building their own connections to these services. The open protocol allows any MCP-compatible client to access these capabilities, making AI assistants significantly more powerful and useful in practical scenarios. And let's not forget MCP integration with social media platforms. While the Model Context Protocol is still relatively new, there are emerging examples of how it's being integrated with social media platforms. Here are some current and potential applications of MCP for social media. Current social media MCP integrations. A. Slack integration. Slack has one of the most well-developed MCP integrations currently available. The Slack MCP server enables AI assistants to access channel history and messages, search through conversations, post messages to channels, manage channel settings and permissions. This allows AI assistants to help with team collaboration, summarize discussions, and respond to queries about past conversations. B. LinkedIn data access. There are community-developed MCP servers that allow limited access to LinkedIn data, enabling AI assistants to retrieve basic profile information, search for companies and job postings, access public content from particular users or organizations. C. Data retrieval from X, formerly Twitter. Community developers have created experimental MCP servers that can fetch recent tweets from specified accounts, monitor hashtags and trends, retrieve basic engagement metrics. What are the potential future developments in MCP? As MCP adoption grows, we can expect more robust social media integrations. 1. Cross-platform content management. MCP servers could allow AI assistants to post consistent content across multiple platforms, monitor engagement, and suggest improvements. 2. Engagement analysis. AI assistants could connect to multiple social platforms to provide comprehensive analytics about content performance, audience growth, and sentiment analysis. 3. Community management. MCP could enable AI assistants to help moderate comments, identify problematic content, and manage community interactions across platforms. 4. Competitive intelligence. By connecting to public social data, AI assistants could track competitor activities and provide market insights. 5. Personalized content recommendations. MCP servers could enable AI to analyze a user's social media activity and recommend content creation strategies tailored to their audience. The open nature of MCP means that developers can create servers for any social platform with an API. While many current social media MCP integrations are community-developed and somewhat limited in scope, we can expect more official and comprehensive integrations as both MCP and AI agent technology mature. The standardization that MCP provides will be particularly valuable for social media management, as it will allow AI assistants to work with multiple platforms through a single, consistent interface, rather than requiring custom integration for each platform. Let's look at real-world examples of RAG in action. Retrieval Augmented Generation, RAG, has been widely adopted across industries to enhance AI systems with external knowledge. Here are some concrete examples of how RAG is being implemented in real-world applications. Number 1. RAG use for enterprise systems integration. Companies are increasingly using Retrieval Augmented Generation to connect language models to their ERP systems. For example, SAP Knowledge Assistant. SAP has implemented Retrieval Augmented Generation to allow employees and customers to query complex SAP documentation and ERP data through conversational interfaces. The system retrieves specific documentation, configuration guides, and real-time data from SAP instances. Oracle Digital Assistant. Oracle has enhanced their digital assistants with Retrieval Augmented Generation capabilities that can retrieve and reason over data from Oracle ERP Cloud, providing contextualized responses about inventory, supply chain, and financial data. Microsoft Dynamics Copilot. Microsoft's Business Application Suite uses Retrieval Augmented Generation to allow users to query their Dynamics 365 data in natural language, retrieving relevant business information and generating reports based on live ERP data. Corporate databases. RAG is being implemented for accessing traditional database systems as well. JP Morgan's Index GPT. The investment bank built a custom RAG system that can search through and retrieve information from their vast financial databases, answering complex questions about market data, research reports, and financial metrics. Legal document analysis. Law firms are using RAG to connect LLMs to case law databases, allowing attorneys to query millions of legal precedents and documents to find relevant information for current cases. Healthcare provider systems. Medical institutions are implementing RAG systems that can retrieve patient records, treatment protocols, and medical literature to assist physicians with diagnosis and treatment decisions while maintaining compliance with health data regulations. Number 2. Vector database applications. RAG is being used to access data-rich vector databases. Vector databases are specialized databases designed to store, manage, and efficiently search high-dimensional vector data, enabling rapid similarity searches on unstructured data like text, images, and audio. Here are a few examples. Walmart's product search. Walmart has implemented a RAG system using vector databases to improve product search and recommendations, retrieving relevant product information based on customer queries that goes beyond simple keyword matching. Spotify's content discovery. Spotify uses RAG with vector databases to enhance podcast and music discovery, retrieving content based on semantic similarity rather than just tags or metadata. Bloomberg's financial analysis. Bloomberg has implemented RAG with specialized vector databases to help financial analysts retrieve relevant financial data, news, and reports when researching investment opportunities. GitLab Documentation Assistant. GitLab's AI assistant uses RAG with a vector database containing their entire documentation corpus, allowing developers to get precise answers about GitLab features and troubleshooting. Number 3. Graph database implementations. Graph databases store data as interconnected nodes, entities, and edges relationships, prioritizing connections and enabling efficient queries based on relationships. Unlike relational databases that focus on tables and structured data, graph databases excel at navigating relationships and are powerful for complex network analysis and have highly flexible schema, whereas vector databases are ideal for similarity searches as they are highly efficient with high-dimensional data and can handle large datasets well. Here are some examples of RAGs being used for accessing graph databases. AstraZeneca's drug discovery. The pharmaceutical company uses RAG with knowledge graphs to help researchers query complex relationships between compounds, proteins, diseases, and research papers, accelerating the drug discovery process. Financial fraud detection. Major banks have implemented RAG systems with graph databases to help identify potentially fraudulent transactions by retrieving and analyzing relationship patterns between accounts, transactions, and entities. Neo4j's Knowledge Graph RAG. Neo4j has developed a RAG implementation that leverages both the semantic power of vector search and the relationship intelligence of graph databases, allowing more contextually aware retrievals. Supply chain optimization. Manufacturing companies are using RAG with graph databases to optimize their supply chains, retrieving information about relationships between suppliers, transport routes, and production facilities to identify inefficiencies or risks. Number 4. Hybrid RAG approaches. Many of the most sophisticated implementations combine multiple storage approaches. For example, Palantir's AI platform. Palantir has integrated RAG capabilities into their enterprise platforms that can simultaneously retrieve information from structured databases, document stores, vector embeddings, and knowledge graphs, providing comprehensive context for complex questions. ServiceNow's Now Assist. ServiceNow has implemented RAG across their IT service management platform, retrieving information from tickets, knowledge bases, configuration management databases, and user documentation to help resolve IT issues. Morgan Stanley's Wealth Management Assistant. Morgan Stanley developed a financial advisor assistant that uses RAG to retrieve information from diverse sources including client portfolios, investment research, market data, and financial regulations. These examples demonstrate how RAG is being used across industries to enhance AI capabilities by grounding language models in enterprise data and specialized knowledge bases. By retrieving relevant information before generating responses, these systems provide more accurate, up-to-date, and contextually appropriate answers than large language models could provide on their own. In conclusion, as we've explored throughout this presentation, MCP and RAG represent complementary technologies that are fundamentally reshaping what's possible with AI. MCP standardizes how AI connects to external systems, while RAG provides the methodology for retrieving and incorporating knowledge from external systems, such as structured and unstructured corporate databases and other document repositories. Together, they enable AI systems that can not only understand our questions, but also access the most current relevant information and take action in the real world. In this video, we've examined how MCP functions through its client-server architecture, allowing AI assistants to access everything from local files to specialized industry tools. We've seen RAG's implementation across enterprise systems from SAP to Oracle, spanning multiple database types including vector and graph databases. We've looked at social media integrations with platforms like Slack and LinkedIn and explored potential future developments. We've demonstrated how both MCP and RAG is being adopted across industries, from pharmaceutical companies accelerating drug discovery, to financial institutions enhancing wealth management, to retailers improving product search. As these technologies continue to mature, we're witnessing the emergence of AI assistants that combine the reasoning capabilities of large language models with the practical utility of having accurate, up-to-date information and the ability to interface with our digital ecosystem, with the potential to become truly autonomous and agent in their deployments. The future belongs to agentic and autonomous AI systems that can seamlessly integrate with real-world data, creating experiences that feel less like interacting with the LLMs and more like working with a knowledgeable, capable PhD-level assistant. Thank you for watching. We hope you found the video informative and engaging. Please stay tuned to our channel for the latest updates and insights from the world of AI. Don't forget to like, share, and subscribe for more exciting content.